hello everyone. Thank you very much for joining us here today. You are in the right place if you are here for our webinar, Practical High-Speed Design, Part 1. This is one of a three-part series that we put together for you here at 9.Connects. This webinar will be given by Sean Kelly, who is an expert in the field of high-speed design. He's presented in the past recently on the topic of impedance, which is a major component of high-speed design. So if you are interested in those webinars, let us know, and we'll be more than happy to make those available to you. But for now, let's focus at the webinar on hand. I will turn this over to Sean. Actually, before I do turn it over to him, I just want to let you know that we will have time for Q&A today. So do please type in your questions in the questions box in the GoToWebinar panel. And we do ask that you be very specific so we don't have to try to get a follow-up question with the limited time that we have. And with that, I will turn it over to Sean Kelly.
Good afternoon, everyone. Thank you very much for joining me today. In the last several webinars that we've talked about, we've talked a lot about theory. And so I was asked to basically give a webinar that says enough about high-speed theory already. Let's give you guys something that you can really work with. And so that was the reason why we're starting this webinar series. Now, the previous webinars laid the groundwork for basic understanding of things like transmission lines, S21, and characteristic impedance. If you want to contact us so that you can watch those webinars, 9.Connects can be more than happy to share those with you. This series is to give you practical understanding and solutions relative to high-speed designs. With that in mind, the structure of this presentation is actually going to be broken up into 3 sections. Today's going to be stage 1, where we're going to talk about PCB material properties, the problems they cause, and then understanding how to minimize those issues. The second stage is going to be talking specifically about PCB routing concepts and the issues you're going to have to deal with doing proper routing. Stage 3 is going to be PCB material selection and stack-up options. Probably one of the more confusing aspects. So that's we're going to help you with that. Now, a real quick review. We talked about in before how current flow is electrons going away from voltage source, and the positive charges are going back towards the voltage source. We also talked about transmission line basics, how we have a distributed inductance and capacitance. And we talked about the concept that actually when you want to think about high-speed design, it is best to think about wave propagation. With that in mind, we really stressed that the signal is really the wave propagating between conductors. And if you always follow that thought pattern when you're routing or trying to figure out how to put a via, if you will keep this in mind, it will get rid of a lot of problems that you'll have. So what do we mean by high-speed design? We mean that we're talking about frequency content versus wave shape. We went pretty detailed in the fact that a Fourier series talks about you needing the 3rd, 5th, and 7th harmonic of that fundamental frequency in order to get a nice square wave. And if you have that frequency content, then you have nice eye diagram. Eye diagrams are used to show how well you have effective high-speed designs. We talked about S21 and how it relates the output signals to the input. And then we talked about characteristic impedance, how important it was for you to have proper matching impedances. So all those are covered in the previous 2 webinars I did. And then last but not least, we talked about the frequencies used nowadays. And that if you look at USB 3 generation 2, then that fundamental frequency being 5 gigahertz means that you really need to have a transmission line that needs to be designed to handle up to 25 gigahertz at a minimum. That's really high frequency, and so a lot of people aren't used to that. So why do we want to talk about the PCB effects? In the essence of high-speed design, we want to make sure that the load sees what the source generated. The PCB is the most used medium, but it is often the least understood. So we want to understand why certain aspects of PCBs cause degradation to the signal. We want to quantify those effects and minimize the impact. The essence of high-speed design, making sure the load sees what the source generated, means that we want to talk about differential for the most part for high-speed design. But in order for you to truly understand differential, we're going to start using just a common microstrip transmission line. This will allow me to communicate the basics in order to make it easier for you to understand the complicated differentials lines in future discussions. So, the question is, do we want to give you the dessert or main course first? You know, I could just give you all the key thoughts and be done with it, but that would be akin to eating dessert before the main course. There is a good chance that you won't remember the key thoughts and definitely not understand the deeper meaning of why they are important. So let's dig into the meat of the subject. So the first question we want to talk about, and we want to just ask your opinion, is, if you don't mind, and we want you to share something with us. If you would read that question and then answer the questions. We won't divulge what you do or say, and we would just like to kind of see what you all have as a background. Interesting. It would look like we got the largest percentage deals with just pencil, paper, and a calculator. Oh, 23% of you all use Hyperlink's SI Wave or some comparable software. Very good. Okay. That helps us in the future have a better understanding of how we can tailor our conversation in these webinars to you. Okay, so PCB material behavior. Over the next few slides, we're going to be talking about charged particles within the PCB material as it relates to the molecules that make up the dielectric. So one of the other questions we want to ask before we get started is to help me better understand what you all know specifically about the material is, what is a dipole moment? So we got one more question for you, if you don't mind indulging me in this one. We're going to go ahead and post that question. If you don't mind, give us an idea of what you think a dipole moment is. And this is going to be important because this is going to be quite a few of the next slides and helping you all to understand the importance of the dielectric constant that you all so often see related to board materials when you're selecting it. Oh, this is good. So 41% of you all knew that the answer was A. Excellent. And it's interesting that it has nothing to do with the magnetism. It's all related to the electric field. Okay, great. So what do I mean by a charged particle? Well, a charged particle is either going to be negative or positive. And for an example, you all probably already know that an electron has a negative charge. With the electric field, it's going to radiate away from a positive charge, and it's going to radiate toward a negative charge. Most of us already know that opposite polarities attract and will create a shared field. This, by definition, creates a dipole moment. Now, linked here in really nice website to go to if you want more information on what a dipole moment is. They get a little more technical than I do. So in a basic atom, we got a hydrogen and a fluorine over here down in the bottom of the screen. You're going to have one proton and one electron, so you have a dipole moment in a basic atom. But when you have a molecule like what you see below, each atom is going to have a certain electron negativity value. And the higher that value is, the greater the attraction of those valence electrons is going to take place. In the example below, the electron negativity of hydrogen is 2.2, and for the fluorine it's 3.98. So what that ends up meaning is that you have those valence electrons are going to migrate over to the fluorine and away from the hydrogen, creating a net charge differential between the two atoms. That net charge difference with respect to the hydrogen is going to create a dipole moment because you basically are creating an electric field between the two atoms. So let's talk about terminology here. Permittivity versus dielectric constant. Both of these are basically synonymous, but it is a measure of the resistance that is encountered when forming an electric field in a medium. Permittivity is connected to the energy stored in the electric field. The permittivity, denoted here by epsilon, is a function of two different variables. One is a constant, epsilon naught, and it's a permittivity of a vacuum, and it's in farads per meter. The epsilon r, this is the one that we're going to be almost talking about exclusively, and it is the relative permittivity of the dielectric. In the world of PCBs, we often use the term dielectric constant. It's almost in all the literature, and that's all you ever see. And even though the dielectric constant is truly synonymous with the permittivity, strictly speaking, the characteristic that we should be referring to is relative permittivity. And keeping that in mind offers less confusion when you're understanding all the general equations. So what is the relationship between permittivity and a dipole moment? A polar molecule, I've got these little things over here, these are polar molecules, is where one end has a positive net charge and the other has a net negative charge due to the arrangement or geometry of its atoms and their charge density, just like we talked about the hydrogen and fluorine molecule. That difference in polarity is going to create that own E field. I denoted that by an orange arrow. It's going to be important to note the color. Therefore, the polar molecule has a dipole moment. In general, the material is going to be made up of some lattice or composition of these molecules or atoms, and if the relative permittivity of that dielectric is greater than 1, then the dielectric's molecules will have some sort of dipole moment overall. It's important to understand that the magnitude of that moment vector is going to be proportional to the relative permittivity value that you see in the material data sheets. In the absence of an external electric field, these molecules will align them randomly. Got another polling question for you. So how do you think the E field strength is related to the relative permittivity? Interesting. We said 37% said inversely proportional, 59% directly proportional. Oddly enough, it's inversely proportional. And we're going to show that. Thank you all for voting on that. You know, oddly enough, when I first started getting into this type of material, no pun intended, but I actually thought the same thing. I thought it was directly proportional. Now, so if we put this material in an E field, this dielectric material here that has these dipole moments, we're going to use a typical case of a basic capacitor because we all know this, what a capacitor behaves like. You'll see that the molecules are going to align such that the charge density is aligned with the capacitor's charges. So if I got the top plate equaling with positive charge and the negative plate down here with at the bottom, you notice that the molecules' charge densities are what align first. Now notice that the E field is in blue is opposite of the orange arrows. This is going to create a problem because now these dipole moments are aligned opposite to the capacitor's E field. This opposite vector is what reduces the net E field between the plates. So it is also why increasing the relative permittivity increases the capacitance. So in a capacitor, again with the positive charges on the top and the negative charges on the bottom, the E field measured in volts per meter is related to the charge density divided by that permittivity. So there you see that the permittivity mathematically is what causes an inverse reaction to the E field. Now the charge density as a function of that sigma is the charge divided by the area. If we combine and reduce, you can see that the E field general equation shows permittivity is in the denominator on the right-hand side. Therefore, the E field is inversely proportional to the permittivity. But now you understand why, because it's the the molecules that make up that FR4 or the Teflon that decrease the ability of that E field to exist. For capacitance, you can see that generally speaking, it's related to the area times the permittivity divided by that distance. And so therefore the capacitance is proportional to the permittivity. Now, what is a PCB anyhow? A PCB is made up of at least one conductive layer and one substrate. Most PCBs today have at least two layers, basically a big capacitor. Most PCBs today have at least two layers, one etched with traces, then we have capacitors and inductors, and we have traces on top and reference plane on the bottom, typically ground. Just a note here, the bottom does not have to be ground. It can be a power plane, and a power plane can serve as a reference plane if done properly. Now, in this microstrip picture below, I want you to notice that we have a conductor on top, the conductor on the bottom, and the insulator in between. So I got one more poll for you. How many capacitors and inductors do you see in this microstrip? And this is going to be critical to understanding what you're dealing with in high-speed design because of both the parasitics and the actual design of trying to get the signal from source to end. Very interesting. So the majority of you think there's one capacitor and two inductors. You know, generally speaking, you could, I can see where you might come up with that answer, but let me explain why, in my mind, I want you to help or understand that D is more accurately describing the proper answer. So when we look at a microstrip, it's actually made up of two capacitances and two inductances, and this is why. When we look at the microstrip, sitting here on top of my dielectric, separating it from the reference plane, because there's a capacitance that's a function of the bottom of the microstrip through the substrate only, that's one capacitance. But from the side view over here, sides and the top, my electric field actually has to go through two different permittivities. That creates a separate type of capacitor value. And that's why I put in there that there's two answers. And this is going to become even more important when we get into strip line design or embedded microstrip. It will also become important when we get into differential routing. So technically speaking, the answer number one, B, was not really wrong per se, other than you had to understand that there were two different capacitances because there's two different dielectrics. A lot of people don't think about, even the solder mask has a specific dielectric permittivity or dielectric constant, and so you got to be aware of that. The microstrip itself and the reference plane will create their own inductances. So it's good to see that so many people saw that there were two inductors. So if you're looking at basically an equivalent diagram of the microstrip, you have this top piece of copper here is its own inductor, and then the ground or reference plane is its own inductor. And then you have the capacitance of the dielectric material itself, and then the dielectric material, substrate, and air. Now here's some of that, let's get to the meat kind of thing, the practical application. So here's an example of an E field inversely proportional to the permittivity in two different substrates. Now I used HFSS for this to show you all how the E field is dependent upon the permittivity. So in this top diagram, everything was just done with the same shape, making sure that I maintain the proper impedance matching to the port. So in this top example, I used FR4, which typically will have a dielectric constant of about 4.4. Notice the lack of the red concentration here underneath the edges of the microstrip, and also the field doesn't seem to radiate out as far here. And then to make it easier to visually see the impact, instead of using, let's say, a Rogers 4003 material, I just made the dielectric air. It gives me a better visualization. You can see actually now that air, of course, the effective permittivity is 1, relative permittivity is 1. So you can see the greater red here, indicating that the E field is actually stronger. So the question is, why does using a lower permittivity material decrease the insertion loss in the S21? Because ultimately, as we talked about in previous material, the S21 helps us to understand how much signal is being lost from the source to the load. Ideally, we want all of the energy coming from the source to get to the load, so we want to minimize this S21 insertion loss. So far, we've been talking about a static E field, but that is not what we're trying to resolve in high-speed design. We have to consider the fact that the field is oscillating back and forth. Because of that, the molecules in the material are going to oscillate its dipole moments, and that takes work. Lowering the relative permittivity decreases that work. Less work, changing those moments, will then leave more energy to propagate. Now, the second aspect of material property when you're picking a PCB has to do with the term called loss tangent. Dielectric loss quantifies a dielectric material's inherent dissipation of electromagnetic energy. Dielectric loss is parameterized in terms of two different terms. One is called a loss angle, small lowercase delta, or a corresponding loss tangent. Now, in the literature, when you're looking at PCB materials and you're trying to select them, they use a term dissipation factor. So dissipation factor is synonymous with the loss tangent. That loss tangent is defined as the ratio or angle in the complex plane of the lossy reaction to the lossless reaction. So if you'll notice down here in the lower right hand corner, we have a picture of a capacitor dealing with ESR, and then we have the reactance of that capacitor. Notice that their delta, their angle they're measuring, is between the imaginary axis and the real. It's not on the right side that you typically would think about. Since we're familiar with capacitors, and we've discussed the fact that a transmission line includes a distributed capacitance, we're going to use a capacitor to understand what this phenomena really is. So delta being that angle between the impedance vector, that's ideal, lossless, and the actual lossy part of the impedance, the ESR. Now we all know that X sub C is going to be a fixed value at a given frequency, but we don't know that ESR is. In a perfect world, ESR would be 0, and therefore the loss angle would also be 0. You may remember from trig that the tangent function is sometimes thought of as the rise over the run. So as you're looking at this equation from the side view, the rise is the ESR and the run is the minus J angle. So why does a PCB material dissipation factor, well, this is why the dissipation factor tries to approach 0, is because therefore the ESR is basically 0. So now what does the permittivity have to do with the loss tangent? So ESR is a derived quantity representing the loss due to both the dielectric's conduction electrons and the bound dipole relaxation phenomena. Since X sub C is inversely proportional to permittivity, then as epsilon decreases, then X sub C is going to increase. If we go back to that previous slide, basically if ESR is a function, a static function, and we increase X sub C, you can see that this angle is going to have to decrease because the rise stays the same, but the run, it goes longer. So the loss tangent, since it's defined as the ESR over X sub C, when we substitute the equation back in there, you can see that ESR times 2 pi permittivity area divided by D. You can therefore see that the loss tangent is directly proportional to that permittivity. So your first dessert, rule number 1, you want to lower the relative permittivity or the dielectric constant of the PCB material you're going to try and select for high-speed design. What you get out of that is a greater E-field strength, which yields lower losses because you're not having to worry about the dipole moments rotating and fighting the E-field being created as that wave propagates. The interesting thing is it usually will decrease with increasing frequency. And the other thing is interesting is that it falls with increasing temperature. So be aware of that when you're designing something for really cold weather, you're actually going to start out with a lower permittivity than you thought you would. Now, let's get into a practical example. Since we are aware of the need for the 25 gigahertz signal to be able to propagate from the source to the load for the USB 3 Gen 2, then I'm going to show you the difference on S21 between two different board materials on a 4-inch piece of microstrip with on 031 thickness. My first example is going to be FR4. Again, common permittivity assigned to that is 4.4. Loss tangent is 0.02, and I picked a track width of 59 mils. Again, I wanted to make sure that I had a 50 ohm impedance so I can match the port on my simulator. The second example is going to be a very common material used in high-speed design, Rogers material, RO4350. Notice the permittivities dropped to 3.66, but also notice that the loss tangent really dropped over a magnitude. But also because that permittivity decreased, I had to increase the width of my track to 66 mils in order to maintain that 50 ohm impedance. So here's what we have on the S21, again on a 4-inch piece of material, which is not very long necessarily for some high-speed designs. So when I picked my markers at the fundamental frequency, the 3rd harmonic, and again at the 5th harmonic. Remember from the very beginning of the slides, we had to have those 3 components to create a fairly valid square wave. So you can see the losses that I have on my S21. Now with the Rogers material, notice, now keep in mind it's not the same scale, but notice the markers show significantly less loss at those 3 specific frequencies. So if you'll notice at 25 gigahertz we had 8.79 loss in dB, and then compared to 2.3. For those of you who might remember that every 3 dB loss is half your power. So that's, you're going to 25% of your power. So that difference in that loss equates to 6.49 dB. Now since insertion loss is a power, we need to convert that to a voltage loss so we can visualize how it's impacting that signal as a voltage waveform, because that's typically when we're looking at an I diagram, you're looking at a voltage waveform. So going back to the equation that we taught you before about insertion loss in dB is 20 log base 10 of the magnitude of S21. If you are working in simulators, you just got to remember that insertion loss is typically shown as a negative, while technically it's a positive because the verbiage is it's a loss. So inherently to the word loss is the negative portion of it. So when we solve for S21 as a voltage, we've substituted in, rearrange, and you get 0.4737. Since by definition S21 is a ratio of the voltage out, that is B2 in the generic equation for S21, to V in, which is the A1 wave, then V out is only 47% of the voltage coming in. That's quite astonishing when you think about it, that you have 47% less voltage on a 4-inch piece of material just because you may or may not have picked the right board material. So what I did is I put this into a spreadsheet that I created so that you can see the different waveforms and visualize the impact. So in my spreadsheet, what I did is I created a conditional switch on S21. So if you want 100% of your signal to get through, then your S21 is a 1. So my conditional switch, if you'll notice here in my spreadsheet, is a 1. Then I have the loss due to the FR4 is taken out of the equation, and I have my generic difference of voltages. You can see my fundamental here is this one right here coming in. Then you can see my third harmonic right here. And the amplitude again is corresponding to the appropriate setup for what the Fourier series calls it out to be. And then the fifth harmonic you see in the yellow. But when you sum them all up, you get this bold black line. That's the sum. Therefore, you can see that we create a fairly good square wave with minimal attenuation. Yes, it has a little bit of ripple in it, but that's desirous. But again, we don't have the seventh harmonic and the ninth harmonic and all the other hot harmonics that are still supposed to be in there that would have calmed that ripple down. Now, if I take that switch and make it so that I want the FR4 loss to be included, then you can see the impact here. Notice, of course, the magnitude of all the three frequency components is decreased now. You can see that we're looking at 87% of my fundamental is present, 66% of my third is present, and only 47% is present of the fifth harmonic. So what that does is, yes, it gets rid of some of the ripple, and at first thought you might think, well, that actually looks like a better waveform. But in reality, it's a worse waveform because I've removed the greater frequency content, and that frequency content is what contributes to the fast rise time. Now, in reality, again, this dramatic, or this, what you see here is even going to be more dramatic in real time if you can actually see all the proper harmonics. So you think about it, okay, 15 to 25, you'd have to have the 35 gigahertz to get the seventh harmonic, 45 gigahertz to get the ninth harmonic. I don't think there's hardly any of us out here that worry about 45 gigahertz. So what I did is there, I created a pseudo I diagram by overlaying the two sums. And so the conclusion you can see here is that the lower relative permittivity and the lower loss tangent gave you not only a faster slew rate, but it also gave you an overall maximum amplitude. The greater bandwidth is what we're after here. So when people talk about, well, my trace or my board material doesn't have sufficient bandwidth, this is what they're referring to, is you're attenuating too much of those higher frequencies. Now, to relate all this to condensed practical understanding, as you interact with different PCB materials, you now have a better understanding of why you would want a lower relative permittivity anytime you are concerned with the attenuation of those higher order harmonics, so that you have the proper square wave transmission being accomplished. You can now also understand how important the lower loss tangent is to that same success, since it can have a huge impact on the loss of those same harmonics. So that concludes most of the material. We're going to have a couple questions here and talk about next week's or the next presentation. So if you don't mind, I would really appreciate you taking a few seconds. Let me know what you think about the material and how it met your expectations. Awesome. So 69% of you all found what I did today was relevant to your needs. That just makes my day. For those of you who voted for C, sorry I was over your head. I try to make sure that it's not too detailed, because I know I've been to quite a few of these kind of webinars, and it seems like people like to throw up really complicated mathematical formulas, and it just doesn't do anything for most of us unless you spend a whole lot of time talking about the equation itself. So I try to minimize that. Okay.
Well, Sean, thank you very much for your presentation here today. We'll give you a couple of minutes to take a look at some of the questions. And of course, if anybody wants to throw in a question there in the questions panel, feel free to do so. We're just going to go over a couple of slides here regarding 9.connects. So you are here today for a reason, because we know that topics of this nature are indeed important to you. And let's face it, high-speed design is definitely the future, but we also know that high-speed design is not something that's very simple to do. As you can see here, and as I mentioned very early on, and I think Sean's reiterated this as well, the fact of the matter is it's not something that you can talk about in one single hour. And if somebody's going to do that, they're going to have to rush through it. Sean's already given 2 presentations on impedance design, or pardon me, the impedance aspect of high-speed design. And again, if you are interested in those, let us know. We'll be more than happy to get those video links out to you. And of course, this is a part of a 3-part presentation. So the next time, Sean's going to be going into more routing aspects, and then on the 3rd part, he's going to talk about very specific board stack-ups. So the point is that you shouldn't feel like you're out there on your own. And I know what that feels like, and you've probably been there at some point too, where there's a time rush, there's a lack of knowledge because it's something new and something different. Of course, there's a cost that's involved with possibly making mistakes and respins out there. But that's why we are here at 9.connects. We are a PCB-centric organization dedicated to training, coaching, design, layout, pretty much any aspect of the printed circuit board that you do need some assistance with, and its related topics. And what do we mean by related topics? We're talking about things like high speed, RF, power, DFM, which is designed for manufacturing, libraries, mechanical, and much, much more. There's more than I could possibly put in this particular slide here. So if you are looking for some assistance, we are there for you. We do want you to get beyond your technical hurdles. We want to be able to confront those technical hurdles with you. It's not just us throwing a bunch of ideas, hoping the best for you. And lastly, it's also to enable you to ultimately get it done. So if you want some more information, please do contact us here at 9.connects, or check out our website, 9.connects.com. We also recently put out a brand new video. It's a 3-minute video that can specifically give you some details as to who we are, what we do, and hopefully in a color.